Okay, welcome to Chapter 15. This is the first lecture that I'm actually recording for Summer 2 session, so hopefully the technology is working correctly and we get everything right. This is about light and electromagnetic waves, and I just never made a lecture for this during the previous term. I talked about energy in quite a bit of detail, but not light specifically. And by the way, this picture is rather amazing, and it looks like it was photoshopped. It was not photoshopped. It was an image captured with a long exposure of about 1 second with a dancer and a photographer named Eric Pare. You can check out his website, Eric, well, it looks like Pare, P-A-R-E, Eric Pare, or Pare.com. I don't know if he's French or French-Canadian, but very simple techniques of lighting, just very clever and very artistic. So I thought that was a nice beginning slide to talking about what light is. And light is part of the electromagnetic spectrum. So there are waves of light bouncing off of me and into the camera, which allows you to, well, it gets transmitted digitally, and then it's coming out of your computer screen, which is a source of light. But everything that you see around you is because light waves are bouncing off of it, or it is emitting light. So it's either reflecting light or emitting its own light. And there are lots of waves, electromagnetic waves, that we don't see. So just going a little bit beyond what I see, I don't see the ultraviolet waves, I don't see the infrared waves, even though they're there. But I also don't see gamma rays, X-rays, ultraviolet, radio waves, microwaves. All these are part of the electromagnetic spectrum, bouncing off of me, some of them going through me, some of them passing by, and some of these wavelengths are very, very large, some of them are very, very small, and light is just a very small slice of the electromagnetic spectrum that our eyes have receptors for, so that our cells are sensitive to, and they send a nervous impulse to our brain. So here's the electromagnetic spectrum, and radio waves can be huge. Radio waves can be bigger than a football field, and then a smaller radio wave is maybe this big, someplace in this range. You get smaller and smaller and smaller, and when you get to about this small of waves, you're talking within the infrared, radiation that can come from sunlight. And then you have this tiny slice that we blow up to show 700 nanometers is 7/10 of a millimeter. 7/10 of a millimeter. So, micrometer versus nanometer. 700 micrometers would be 7/10 of a millimeter. 700 nanometers would be 7/1000 of a millimeter. So if you were to take a millimeter and divide it into 1,000 slices, that then 7/1000 of those would be the wavelength that you can start to see. So between 4 1,000ths of a millimeter and 7 1,000ths of a millimeter approximately is what you have receptors for, that you have cells that respond to those wavelengths. And you have different cells in your retina that respond to different parts of this spectrum. And so it registers in your brain as different colors. And an interesting thing is that while you and I can agree on saying, oh, this is red, and we can measure with an instrument and say, oh, that's 750 nanometers of wavelength. That's the size of the wavelength. So we both say, oh, yeah, that's red. But the interesting thing is, I don't know if your red looks the same as my red, because there's actually no light hitting the brain, is there? The light's coming into the eyeballs, but the eyes are transmitting just an electrical chemical message into the brain, and the brain has to construct an image, an artificial image of the world. based on this data that's coming in. And so there's no reason other than the fact that we're related and our brains are structured similarly, but I really don't know if your red looks the same as my red. We'll both call it red, but if I could get inside your brain, I could look and say, oh, no, that's not red, that's green. Because it could look, what's red in your brain could look green in my brain. That's kind of just a weird thing to think about. Anyhow, so we have red, orange, yellow, green, blue, violet, this spectrum of visible light. And then below that, we have the ultraviolet. Above the red, we have the infrared. And then below ultraviolet, we start getting into X-rays, which are even smaller, and gamma rays, which are much smaller. Now, as we get smaller and smaller wavelengths, we get higher and higher energy and higher frequency. Higher frequency, higher energy. So let's define a couple of terms. Let's just say that all of these wavelengths in the electromagnetic spectrum travel at the speed of light. So they're much faster than sound. Light waves and radio waves and X-rays, they are all part of the electromagnetic spectrum, and they all go the same speed, which is about 186,000 miles per second. And that's extremely fast. So think of tall people and short people and little tiny kids if they were all walking at the exact same speed. Okay, so a really tall person walking, say, 3 miles an hour, boom, 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 boom. They take big steps. Okay, so this would be like a low frequency wavelength. A long wavelength would be low frequency. The frequency is how often does it pass a particular point. But you can think of the frequency kind of as like the length of the footsteps, or the wavelength. So a really tall person can take really big steps, boom, 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 and a really small person has to take a whole bunch more steps in the same time to go the same speed. So this is why these high frequency the small wavelengths have a high frequency. It's little tiny steps to go the same speed as these really great big steps. So think about this. Here's a step. Here's a radio wave that is the size of a football field. So it takes it goes that whole football field in one step. And here's something that is 1,000th of a 1,000th of a millimeter. And so how many billions of steps is it going to have to take to cross that 100-meter field? Okay, many, many. So anyhow, hopefully that's helpful. So the wavelength is just, we measure from crest to crest or from trough to trough. That tells us the wavelength, and we measure it just on the metric system. I mean, we could measure it in inches and feet and stuff, but that would just be confusing because metric system is much, much better. We just divide everything, divide by 10, divide by 10, divide by 10 as we go down. We don't have to. So anyway, it's just measured in meters for the really long ones, and then centimeters, and then millimeters, and then down into, we kind of skip over micrometers, get right into nanometers. But anyway, frequency is how often does it pass a certain point. So with a wavelength that does this, you get quite a few in 1 second. A longer wave, it just passes maybe one time in that second. So long wavelengths have lower frequency. Short wavelengths have higher frequency. The short wavelengths with the high frequency have the higher energy as well. And so the effect of that is that, high frequency, well, they just behave differently on tissues or passing through buildings and things like that. Okay, so this inverse relationship just means that when one goes up, the other goes down. So as wavelength goes up, okay, as you get longer and longer wavelengths, your frequency decreases. Okay, it's the giant person taking big giant steps, so you don't need as many steps to cross that area. As wavelength decreases, little teeny tiny person, miniature person, little tiny steps, the frequency of steps goes up. Okay, so we mentioned that you're seeing light all the time, and it's either coming from something, a source of light, or it's reflected off of something. And natural sources of light would be like the sun, that's the main one, but fire or fireflies, they make their own light. Not the moon. The moon is just reflecting sunlight. So it's just a bright surface that it reflects a lot of sunlight, but it doesn't emit its own light. It doesn't create light. Other sources of light can be artificial, like your computer screen or your cell phone screen, or fluorescent lights or incandescent lights. Those are all sources of light. They're putting out this electromagnetic radiation. And then that light goes and bounces off of things and gets absorbed by them. So I have a black shirt on today, and basically it's absorbing all the light that's hitting my shirt. That's why it's black. It's not reflecting anything else. If I had a yellow shirt, I could say, well, I'm reflecting everything but the yellow, and it's the yellow that's bouncing back. If I had a blue shirt, I would be reflecting the colors, the parts of the spectrum other than the blue part, and the blue part would be reflected back. So an object, kind of a greenish, yellowish object, this plastic is absorbing the blue part and the red part of the spectrum, but not the greenish yellow parts. It's reflecting those back. And well, it's plastic, it's transparent, so maybe the blues and yellows, maybe the blues and reds are actually passing through it, and the yellow is reflecting back. So this is a fairly transparent material. It allows most of the light to pass through. I can see pretty well through it, but it doesn't let all the light through. It doesn't let that yellowish greenish light through. It's bouncing that back. And so there are lots of things that light passes through pretty well. Air, clear glass, clear water, and then translucent materials let some of the light through, but not enough to make a clear image. So frosted glass of a bathroom window, or I don't know, just a sheet of paper, that's, I can hold that up and I can see some light coming through it, but it's not too much, so it's translucent. And it's getting to the point of opaque. Something that's opaque, I cannot see through this at all. I can't see through it, so it's opaque. It doesn't let the light through. It's absorbing and reflecting that light. Now, as it absorbs the light, it absorbs it and it's converted into heat. Now, when I touch this object, I'm like, well, this isn't hot. No, it's not, but there's just not that much light energy hitting it. If I was outside in the sun, this would be warmer to the touch than a white surface because it's absorbing. The white surface would be reflecting. And your car in the sunlight, I should mention that quickly, the light waves pass through the glass easily, and then they get absorbed on the surface of your car heats up. It does reflect light as well. I mean, your car is not just a black hole, it's reflecting light back out, but the wavelengths that are being reflected are not the same wavelengths that were coming in. It's not the same frequency, and they don't pass through the glass as easily. And so, yes, some of the light gets out through the windows, and so some of the energy that went in also comes out, but not all of it. Some of it bounces back off the inside of the window and back into the car, and you get a net gain of energy, of heat in the car. It's a greenhouse effect. So we mentioned that light travels very, very fast, 186,000 miles in a second. So that's about 7 times around the Earth in a second. Light's not the only thing that travels this fast. Again, X-rays, radio waves, they all travel the same speed. And the electrons circling around atoms in everything's made of atoms that when you look around it, the electrons are also moving at light speed. What are they doing moving at light speed? I don't know. I don't know how they do that, how they keep it up continuously. It's weird. Okay, so we cannot travel anywhere close to the speed of light. We can travel faster than the speed of sound, which is cool, but that's really slow compared to light. So the light year, how far does light travel in a year? That's called a light year or a parsec. If you want the Star Wars reference, parsec. Anyway, it's about 6 trillion miles in a year, and our sun is not a light year away. It's only 8 light minutes away, right? It takes 8 minutes for the sunlight to get to us. So that's only a mere 93 million miles away. Our nearest star besides our sun is part of the Alpha Centauri group. So it's called Proxima Centauri. It's about 4.25 light years away. Take about 148,000 years in the space shuttle to get there. So we talk about, some people say, oh, you know, if we ruin this Earth, we'll just go colonize another planet in another solar system. Right. The next closest solar system would take us about 150,000 years to get there. So pack a lot of food for that trip. And every generation, Mom, are we there yet? No, dear. You'll have to live, grow old, die. It'll be your children's 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 children. You know, generations later we'll get there. Don't worry. Anyway, so space is just immense. That's our nearest star within the Milky Way galaxy, and there are billions of galaxies, and it just is mind-blowing how big space is. And you have all these stars out there, these trillions of stars. So why is space dark? That's an interesting question, isn't it? Why is space dark? And it turns out that space would not be dark if the universe was not expanding. If the universe was not expanding, space would be totally filled with light. But physics gets really weird when we talk about astronomical scales of things. Anyway, probably we're not going to get visited by aliens. You know, even if you live in Bracketville or Uvalde or Eagle Pass, you're probably not going to get abducted by space aliens. Okay, unless they have some really cool technology to travel faster than the speed of light, which, according to the laws of physics, nothing can travel faster than the speed of light. So we'd have to come up with some new rules to do that. Okay, if something, you know, blocks light, then it creates a shadow behind it, and the umbra is the part that's where the light's totally blocked, and the penumbra is the fuzzy part around where some of the light gets through. Okay, so conditions for you to see anything is that there has to be a light source. So it doesn't matter, you know, how colorful. You can wear a tie-dyed shirt or bright pink or whatever, but if you're in a cave and there's no light at all, it's not going to have any color to it. It's going to be just black. Everything's black. You can't see it. Light has to strike the object. Now, if I'm in a dark room and I shine a light away from me, I can still see things where the light's not hitting. That's because light bounces, and you know, it's bouncing, it's hitting, it's going 186,000 miles a second. It's going to bounce all over the place. Any little bits of it might bounce all over. So you'll get some light, even indirectly. So even though I'm shining the light that way, some of it's going to be bouncing back and hitting me, and so light has to hit the surface of whatever you're looking at. No light coming there, you can't see it. See my eyes, how they're dark in the very center, the pupils. It's not black pigment. The pupil of your eye is just a hole. It's just an opening into the eyeball. So here's the opening. It's dark inside your eyeball. That's why why it looks black. Anyway, the light has to go through that hole, through that pupil. Excuse me. The light has to go through your pupil and stimulate receptor cells in the back of your eyeball, so in your retina. And I added a fourth condition here. You need a functioning eyeball and a brain, and you know, the whole connection. If your optic nerve is cut, you're not going to get a signal. So you know, it's a little bit more than 3 conditions if you want to get technical about it. When light bounces off of something, the angle of incidence, the angle that it's coming in at, equals the angle of reflection. Okay, and that's how it works. If it hits, you know, something that's flat, the angle of incidence equals the reflected ray, or the angle of reflection. So the incident ray, the reflected ray. So this would work fine if you have a plane or flat mirror. So it gives an interesting effect, and you know, as a kid, it takes a little while to get used to combing your hair because the image doesn't look quite right, and it takes a while for you to figure out as a kid, oh, what is my right hand looks like my left hand in the mirror image. You know, and you can hold up a piece of paper and you see that it's, you know, the writing goes from, you know, it gets inverted left to right. And that has to do with the reflection, right? This is not the same. We say that the angle's the same, but no, well, not exactly, right? It's not coming in like this and going back like that. It's coming in like this and going like that. Somebody's trying to contact me. I'm going to pause. Okay, I'm going to actually pause, and I'll stop here so that I can to go home and help with the doctor's appointment. So just a routine thing. But anyway, so I'm going to resume at the scattering of light. And so stopping here for now.